Yeah, what is that? Hello guys, welcome back to my channel. Today we're going to talk about quarks. Is quark like this? Is it as small as that, like the air that you breathe? You breathing oxygen, right? 02. Oxygen is not a quark, it's a gas. And a gas, matter can be a gas, can be a solid, can be liquid. Yeah. So even we breathing matter in form of oxygen, and what comes out of you is carbon dioxide, CO2. You are busy manufacturing carbon dioxide as you live and breathing oxygen. Now, today we're going to talk about matter, a quark. A quark. Something very tiny, really very, very, very small, very, very tiny. It's a fundamental unit of matter. Very, very, the last bottom beyond quark is what we're going to analyze today. Something that makes up this universe, which makes everything. Isn't it strange? This thing, we call it quark. Yeah. Now, what is it? Okay. A quark is a type of elementary particle and a fundamental constituent of matter. Quarks combine to form composite particles called hadrons. Yeah, these are names we are given it, quark, hadron, whatever. No, hadron means a combination of those quarks, the most stable of which are protons, which forms a nucleus, and the neutrons, which form a nucleus, and the components of atomic nuclei. They form the components of atomic nuclei. We don't include the electron here. So that's what a quark is. It's a fundamental constituent of matter. Now, how do they make these hadrons? Most hadrons, which now is a combination of quarks which forms composite particles. Combination of them, they make composite particles called hadrons. Now, most hadrons which are formed from these quarks are made up of either 2 or 3 quarks. So 2 or 3 quarks will make hadron. Now, hadrons made up of 3 quarks, such as proton and neutron, are called barons. B-A-R-Y-O-N-S, barons. Protons contain 2 up quarks and a down quark, while neutrons have 2 down quarks and an up quark. Up quarks are always, up quark is positive, down quark is negative. And the down quark must be negative. If it's negative, it may weigh more than the up quark. Hadrons are made up of 2 quarks. The hadrons made up of 2 quarks are called mesons. Okay, so we have barons and mesons. So, how are they actually created? How are they created? Sometimes it's difficult. Let's pause here. Now we say that quarks are fundamental, elementary particle or fundamental constituents of matter. Now, if you go beyond the quark, is there anything in blank scale, microscopically? Yeah. Well, okay, we're gonna go deep. So, hadrons, any member of a class of subatomic particles that are built from quarks, and thus react to the agency of the strong force. Okay, that's the definition of hadron. Any member of a class of subatomic particles that are built from quarks and thus react through agency of the strong force. The hadrons embrace mesons. Mesons are made of 2 quarks. Okay, byrons, 3 quarks, e.g. proton, neutrons, and sigma particles. And there are many resonances, because when you're talking of these things, you know, all these names you've given them, these are energies. A certain point of it's energy at a certain point. Okay, so what do quarks make? I'm giving you form of questions, and that's very easy for you to understand than just reading to you a long passage. What do quarks make? Quarks make up protons and neutrons. You have known from the hadrons, from the fundamental particles, the byrons, the mesons. So quarks make up protons and neutrons, which in turn make up an atom's nucleus. So you see, it's going up the hierarchy. So the quarks, to the byrons, to the mesons. Now, we are being told that quarks make up protons and neutrons. Of course, to go back to that introduction I've given you, where we have said that quarks is a typical elementary particle and a fundamental constituent of matter. They will combine to make a particle called hadrons, which the most of the stable of them are protons and neutrons, which means protons and neutrons are hadrons, the most stable of the composition of these quarks. Now here we are being told that the quarks, they make up protons and neutrons, of course, because after they make hadrons, then here the hadrons, the most stable of them are protons and neutrons, which in turn make up an atomic nucleus. Okay, so we are made of atoms and nucleus, electrons. Now each proton and each neutron contain 3 quarks, that we have said, and a quark is a fast moving point of energy. This is what I was trying to get. It's a fast moving point of energy. That's what you call a quark. There are several varieties of quarks. If this is the case, then there must be a variety of them. If a quark is a fast moving point of energy, then there must be varieties of that. If you bring in maths, you call it derivatives. The change in motion, how fast they're moving. Are they moving at a constant speed, or are they changing? You know, so that's it. There are several varieties of quarks. Exactly. There are varieties, and these varieties means that the motion, if it's a fast moving point of energy, it must not be constant if a variety exists, because if there's no variety, then it will be a constant. But if there is a variety, unless there are other conditions that can alter this, then, let me come again. If it's a fast moving point of energy, there must be a variety of them. And if there's no variety, it means it's a constant. Now, is energy really constant? No, energy cannot be destroyed, but it can change from one form to another. It can change from one form to another. So now let's go to how fast does a quark move, by the way. Now the velocity of a quark, and I've told you a quark is a moving point of energy. It's a fast moving point of energy. Now, how fast does it move? Now the velocity of quarks within the nucleus is nearly equal to that of light. And you know what the speed of light? Of course, I told you several in the other videos, 300,000 kilometers per second. So that's how fast a quark moves inside the nucleus. It's almost as fast as that. Not exact, of course, almost. It's fast. Now, quarks encounter very rapid change of velocity and turn back sharply. Because there's not one quark, there are 2 or 3. And if we are talking a nucleus which contains protons and neutrons, how many quarks are there? Because a proton has 2 up quarks and 1 down quark. The neutron has 1 up quark, 2 down quark, and it's not one. When you say protons and neutrons make up a nucleus, are they just 2 of them? How many protons and neutrons make up a nucleus? So here's a variety of them, and they encounter change in velocity and turn back sharply, maybe due to interactions that takes place there. Therefore, to calculate their gravitational effect, because it's moving at that fast speed, and you know that there's gravity also. So there's relativity. It's called relativistic calculations are required, because you can't use quantum mechanics here. Something that moves at the speed of light can only be done with relativistic calculation of Albert Einstein. Quarks, like all matters, are affected by Newtonians. You know what Newton says, that everything in the universe is attracting each other matter with a force which is equal to the distance between their masses, and inversely proportional to the distance between their masses, and equal to the proportion of the matter itself. That's one that I remember. Now let's talk about gravitation effects of quarks. Now, quarks move within the nucleon at a relativistic speed. Nucleon, which you know is made of protons and neutrons. Okay, they move at this speed. This causes inertia, and this inertia, you know what's inertia? The forces that resist the change. This inertia results in a gravitational mass effect. For short distances, this is a strong force which you find in the nucleus. For distant objects, it becomes gravity. To analyze that, for long distance, it's gravity. For short distance, it's strong force in the nucleus. So how does a quark change? How does it change? The quark changes. How is that possible? Now, in a beta plus decay, an up quark changes into a down quark with the emission of a positron and a neutrino. You're going to know what these things mean, or maybe I should tell you what a positron is. I'm sorry. I like doing like this. Sorry, I'm sorry about it. Yeah, we want to know what a positron is. Actually, a positron is something that is having the same mass as an electron, but has a positive charge. And a neutrino is something which is like a massless, doesn't have any mass at all. So in a beta plus decay, an up quark changes into a down quark. And you know this decays takes place because of weak force. We did that in the other previous video, not the strong force. It means the weak force is also involved here. So to a down quark with the emission of a positron and a neutrino, while in a beta minus decay, a down quark changes into an up quark with the emission of an electron and an anti-neutrino. The quarks are held together, the nucleus, by the strong nuclear force. That one we have already said. Okay, let us first understand what is a positron. I'm telling you positron, but you must be wondering, what is this called a positron? The names we have given them. It is a subatomic particle with the same mass as an electron and numerically equal but positive charge. So it's just like an electron but having a positive charge. And what's a neutrino? This is very interesting. Neutrinos are the most abundant particles that have mass in the universe. You have heard of neutrinos, and I'm sure. Every time atomic nuclei come together, nucleus, nuclei or nuclear, it's a plural. Nucleus is single. Nuclei seems to me to mean plural. They come together, like in the sun. You know what is happening in the sun. Atomic nuclei are coming together, and fusion is taking place. So every time atomic nuclei come together or break apart, like in a nuclear reactor, you know, in a nuclear reactor they break apart, but in the sun they come together. Yeah. Now they produce neutrinos. When there is a nuclear reaction, like when they tear apart, they form neutrinos. When they come together, like in the sun, they form neutrinos. So even a banana that we eat, the bananas, they emit neutrinos. They come from the natural radioactivity of the potassium in the present fruit, the banana. Banana has a lot of potassium. A neutrino is a fermion, we call it a fermion, that interacts only via the weak interaction and gravity. I told you what's weak interaction in the previous video, weak force. The neutrino is so named because it is electrically neutral. It's electrically neutral. And because its rest mass is so small, that it was long thought to be zero. It has no mass at all. It's called a neutrino. They're abundant in the universe. Now there's a side note to that. What is a beta plus decay? Because I'm telling you beta decay. What is B-A-T-A plus decay? Beta decay. Beta decay, beta decay, how you pronounce it. Now positron emission, which I've told you what a positron is, emission, beta plus decay, or P plus, written like this. Written like this, beta plus. The name I'm trying to pronounce it is because maybe my English pronunciation might bother you. The beta decay, this decay, this is the same thing. It's written like this, or this is the English word for it, beta decay. Beta decay. Now this is positive, you can see it's a positive sign, we are given it. And the thing I'm calling positrons. Positrons emission. I've told you positron, something like an electron, but has a positive charge, which is numerically the same as an electron. So this is a particle you're talking about. So in a positron emission, beta plus decay, beta plus this one decay. Well, do you know what is decay, by the way? It's radiation. When something is giving out radiation, then reducing its mass to become more stable. So that we call it in physics decay. So I'm defining to you a positron emission beta plus decay is a subtype of radioactive decay. radiation. I told you what's radioactive, something energy emitting, a decay called beta decay. That's the name we have given, beta decay. But the whole thing is that this particle is giving out radiation, and the main reason in nature is that when normally these things give out radiation, they assume a more stable state. So let's come again. Positron emission beta plus decay, or beta plus decay, BP, this one is a subtype of radioactive decay called beta decay, in which a proton inside a radionuclide nucleus is converted into a neutron. So a proton is converted into a neutron while releasing a positron and an electron neutrino, VE. Positron emission is mediated by the weak force, because the weak force is responsible for the disintegration or breaking down or radiation. Okay, so I think we'll end it there for today. As I told you, dig deep into atomic nuclei, trying to understand the nature of things, the atoms, the nucleus, what makes up the nucleus, the protons, the electrons, the positrons, the mesons, the baryons, yeah, the anti-quark, the neutrinos, antineutrinos. So you see, now we're coming together and putting all this stuff together so that we can understand fundamentally from the very basic, the roots, how this origin of matter and energy comes into be. The whole question goes down, finally to energy, and that's why we ask really, what is this thing called energy? I've done a video on energy, and you can go back on it and watch it, and try to comment, what's this thing, energy? You know, you say you don't have energy. I don't have energy. So what is that? You feel weak, you cannot walk, I have no energy. When you eat food, you have energy. So energy comes from food. And what does food consist of? We have proteins, neutrons, carbohydrates, vitamins. And what are they fundamentally? What are these things that you eat? What are carbohydrates? You can write an organic chemistry formula for carbohydrates and find there are carbons, there are hydrogens, there, yeah. So this is what we eat, this is what we are made of. But the fundamental question still remains, what is this thing, energy? It cannot change, it cannot be deformed. I mean, it can change from one form, it can't be destroyed. And it was there from the primordial time, before the Big Bang. When we had the inflation, what was causing the inflation is energy. Inflation could not take place without energy. And now, what is this thing? Energy. We just given it the name energy, but what's the phenomenon? You think deeply. You want to think deep. What is this thing? It doesn't have any intuition. I mean, it's not something that thinks like the way you think, but it acts, it affects, it produces, it disintegrates, I mean, into other forms of things. Yeah. So let's not go further, and we're going to fields actually, and quantum fluctuations in vacuums, virtual particles. Yeah, we're going to the mystery of things, trying to understand the nature around us, or the universe that we are part of. So anyway, thanks for watching. Please stay tuned to my channel, subscribe, like and share, and comment. Bye for today. See you again later. Bye. By the way, please subscribe to my channel, you guys. I'm asking you, should I beg you to subscribe? Is it you watching or not? If you're watching, get your friend, tell a friend and a friend to share. let them also watch this great content. Like, please, and share. Bye.